This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion. Today we'll be delving into a research paper focusing on a novel approach to spacecraft attitude control using deep reinforcement learning. The paper proposes a method to enhance the resilience and adaptability of satellites under fault conditions, specifically when reaction wheels malfunction. What are the primary limitations of traditional control methods in this context?
Traditional methods like proportional derivative (PD) controllers, while simple and effective under nominal conditions, struggle with adaptability and fault tolerance. They rely on fixed gains, making them sensitive to changes in system dynamics such as reaction wheel (RW) failures or degradation. When an RW fails, the PD controller lacks the ability to autonomously redistribute torque among the remaining wheels, often leading to instability or complete loss of control.
The paper highlights the shortcomings of existing deep reinforcement learning (PRL) algorithms like TD3, PPO, and A2C in providing real-time adaptability and fault tolerance for autonomous satellite operations. What are the specific challenges these algorithms face in this domain?
These algorithms often struggle with the sparse reward environment inherent in spacecraft attitude control. Successful control often requires many small adjustments, and the reward signal is only significant upon achieving the desired attitude. This sparsity makes it difficult for the algorithms to learn effective control strategies, especially during fault conditions. Furthermore, the high dimensionality of the action space, controlling multiple RWs, can lead to instability during training.
The paper proposes a solution called TD3HD, which integrates twin-delayed deep deterministic policy gradient, TD3, with hindsight experience replay (HER) and dimension-wise clipping, DWC. Can you elaborate on how each component contributes to improved performance?
TD3 provides a stable base for DRL, addressing overestimation bias issues common in other algorithms. HER tackles the sparse reward problem by allowing the agent to learn from failures by retrospectively redefining goals. DWC stabilizes the learning process by independently clipping torque adjustments for each RW, preventing overcorrections that could destabilize the system, particularly during faults.
How does the hindsight experience replay (HER) mechanism specifically address the sparse reward problem in this application?
HER cleverly transforms unsuccessful episodes into successful ones by changing the goal retroactively to match the actual outcome. Instead of only rewarding the agent for perfectly achieving the desired attitude, her rewards progress towards the goal, even if the final state isn't perfect. This significantly increases the amount of useful training data, accelerating learning, and improving the agent's ability to recover from faults.
The paper mentions dimension-wise clipping, DWC. How does this differ from standard clipping techniques, and why is it beneficial in this high-dimensional action space?
Standard clipping applies a uniform threshold to the entire gradient vector, potentially leading to a zero-gradient problem in high-dimensional spaces. DWC, however, clips each dimension of the action space, each RW's torque, independently. This prevents the zero-gradient problem while still maintaining stability by preventing excessively large updates in any single dimension.
The paper benchmarks TD3HD against PD control and other DRL algorithms. What were the key findings of this comparison?
TD3HD consistently outperformed all other methods, achieving significantly lower attitude errors, improved angular velocity regulation, and enhanced stability under fault conditions. The PD controller failed to adapt to the RW fault, while the other DRL algorithms showed some degree of fault tolerance but lacked the precision and stability of TD3HD.
The reward function in TD3HD is designed to minimize attitude error while penalizing high angular velocities. Can you elaborate on the design choices and their rationale?
The reward function comprises three components: a reward for reducing attitude error, a penalty for high angular velocities to prevent instability, and a bonus for achieving high accuracy below a certain threshold. This multi-component design ensures that the agent learns to balance precision and stability, crucial for safe and effective spacecraft control.
The paper uses the Basilisk simulation framework. What advantages does this framework offer for training and evaluating the DRL agent?
Basilisk provides a high-fidelity simulation environment that accurately models spacecraft dynamics and RW behavior. This allows for robust training of the DRL agent under realistic conditions, including RW faults, ensuring that the learned control policies are effective in real-world scenarios.
The paper concludes by suggesting future work on extending TD3HD to satellite constellations. What are the key challenges and opportunities in applying this approach to multi-satellite systems?
Extending to constellations introduces challenges in coordination and communication between satellites. A distributed DRL framework would be needed to enable autonomous attitude management and fault tolerance across multiple satellites. The opportunity lies in developing more resilient and scalable operations for large-scale satellite networks.
The paper mentions the use of importance sampling IS weights. Could you explain their role in the TD3HD algorithm?
Importance sampling is used to correct for the mismatch between the behavior policy, the policy used to collect data, and the target policy, the policy being learned. Because TD3 is an off-policy algorithm, the data used for training is generated using a different policy than the one being optimized. IS weights adjust the importance of each sample in the replay buffer, ensuring that the updates are more accurate and stable.
The algorithm uses a specific torque redistribution strategy when an RW fails. Can you describe this strategy and its importance in maintaining control?
When an RW fails, its corresponding action dimension is clipped to 0, effectively disabling it. The remaining active RWs then receive updated actions based on the redistributed torque. The backup RW is activated only when necessary. This ensures continuous control and prevents the system from becoming unstable due to the loss of one RW.
What are the key advantages of TD3HD compared to other DRL algorithms and traditional methods for spacecraft attitude control, particularly in the context of fault tolerance?
TD3HD combines the strengths of TD3, HER, and DWC to create a robust and efficient algorithm for fault-tolerant control. It addresses the limitations of sparse rewards and high-dimensional action spaces, resulting in superior performance in terms of accuracy, stability, and adaptability to RW failures. This makes it a more practical and reliable solution than traditional methods or other DRL algorithms.
The paper acknowledges support from the SmartSat CRC and Saab Australia. How do these collaborations contribute to the research?
These collaborations likely provided access to resources, expertise, and real-world data relevant to spacecraft attitude control. The involvement of industry partners like Saab Australia is crucial for translating research findings into practical applications.
The paper mentions the use of modified Rodrigues parameters, MRPs, to represent the spacecraft's attitude. Why were MRPs chosen over other attitude representations like Euler angles or quaternions?
MRPs offer several advantages in this context. They provide a smooth and singularity-free representation of attitude, avoiding the gimbal lock problem that can occur with Euler angles. They are also computationally efficient, making them suitable for real-time control applications.
The experimental setup involved simulating a RW failure at a specific time. Why was this approach chosen, and how does it affect the evaluation of the algorithms?
Simulating a RW failure at a predetermined time allows for a control evaluation of the algorithm's fault tolerance. It provides a clear benchmark for comparing their ability to adapt and recover from a sudden and significant change in system dynamics.
The paper uses a specific set of hyperparameters for TD3HD. How sensitive is the algorithm's performance to changes in these parameters?
While the paper doesn't explicitly detail sensitivity analysis, the fact that they report stable and reliable performance with standard settings suggests that TD3HD is relatively robust to hyperparameter variations. The integration of HER and DWC likely contributes to this robustness.
The paper mentions the use of the Stable Baselines 3 library. What are the advantages of using such a pre-built library for implementing DRL algorithms?
Using a pre-built library like Stable Baselines 3 offers several advantages. It provides well-tested and optimized implementations of various DRL algorithms, saving significant development time and effort. It also ensures reproducibility and facilitates comparison with other research.
The paper's results show that TD3HD achieves rapid convergence to the desired attitude after the RW failure. What factors contribute to this rapid convergence?
The combination of HER and DWC is key to the rapid convergence. HER provides a wealth of training data even from failed attempts, while DWC prevents destabilizing updates, allowing the algorithm to learn efficiently and effectively.
The paper focuses on attitude control. Could this approach be extended to other aspects of spacecraft control, such as orbit control or thruster management?
The principles of TD3HD, particularly the use of HER and DWC to handle sparse rewards and high-dimensional action spaces, could potentially be applied to other spacecraft control problems. However, the specific design of the reward function and state/action spaces would need to be adapted to the particular control task.
This has been a very informative discussion on the application of deep reinforcement learning to spacecraft attitude control. Thank you.